Good evening. My name is Jeff Brook-Thorson, and I'm the Associate Director for TIZED, the Trottier Institute for Sustainability in Engineering and Design. I'd like to welcome everyone watching to our SED by 180 Seconds event, which is the last phase of our fall SED Talks presentation skills training program. Before I get started, I want to let everyone know tonight's agenda. I'm going to start off with a few opening remarks, and then we're going to get into the student presentations of their 3-minute talks. And then I'm going to introduce the selection committee who we're selecting for the winter program, which is our 2021 Changemakers program, leading up to our main SED Talks event in the spring. After that, we're going to have an Audience Choice Award vote. And so please make sure to stick around to vote in the Audience Choice Award. And then we'll close with some closing remarks. For those of you who don't know much about the SED Talks training, we created this program back in 2006 in order to highlight the excellent research that's being done by graduate students in the McGill Faculty of Engineering on topics that are important to transitioning our society towards a more sustainable future. In the fall, we open up registrations to graduate students in our faculty who are performing research in any of the areas that fall under the umbrella of sustainable engineering and design. And this year we had over 40 students sign up, which is a new record for us. All of these students received training that includes workshops, small group coaching sessions with feedback, and they explored strategies on how to design research talks that are both accessible and impactful. And these training sessions were offered in collaboration with McGill's Skill Sets program and were led by Dr. Andrew Churchill. This year, due to the ongoing pandemic, we had to adapt how we ran the sessions, and so the primary focus of the fall 2020 training was how to deliver a short virtual talk on their research, which is then forms the heart of tonight's SED by 180 Seconds event. Tonight, you'll hear talks from 13 graduate students from across the faculty who will present their research in 180 seconds. The students had one take to record these talks with McGill's media services last week. And then from among these presenters, a selection committee will choose or has chosen those 3 students, our 2021 Changemakers, who will then proceed to the winter training program, where they'll deliver full presentations at our annual SED Talks event in the spring. At the conclusion of SED Talks, each Changemaker will receive a $1,000 prize, as well as all the specialized training. And we're pleased to announce that the 2021 SED Talks event will be hosted in partnership with WSP, one of the world's leading professional services firms. After the announcement of the Changemakers, we'll have the audience choice poll live, and so please make sure to stick around for that. So without further ado, please enjoy the talks.
To show you a picture. Well, on this picture, you can see explosion. This is the Deepwater Horizon oil spill in Mexico in 2010. This oil spill lasted for 5 months, and the cleanup cost went up to $65 billion. The main cause behind this explosion is simply the gas hydrate formation in the pipe, which can be formed under high pressures and low temperatures in oil and gas industries. Currently, to prevent the gas hydrate formation, we add chemicals such as methanol to shift the gas hydrate from stable region to unstable region. However, these chemicals are actually not good for the environment, and they are not 100% effective. Fortunately, my research is looking for an alternative. There will be 100% effective, and it won't include adding nasty chemicals to destroy the atmosphere. To meet these objectives, I will focus on investigating the stability criteria and the instability mechanism of gas hydrates. For the stability criteria, it will be split into 2 parts, the mechanical and thermodynamic aspects, and they will be approached separately. The mechanical stability criteria will be approached from the atomic level with a simulation performed on the unit cell at equilibrium state and 0 Kelvin with the support from the software VASP. And the thermodynamic stability criteria will be approached from the molecular side. The dynamic processes will be performed at various temperatures with software lamps. And the same methodologies will be applied for the instability mechanisms, which will be split into the crack nucleation and the crack propagation as well. If The stability criteria and the instability mechanism could be studied very well. The gas hydrate formation in the pipes can be avoided. Then the operational safety in oil and gas industry can be guaranteed without any negative impact on the society and the environment. That's all. Thank you for your attention.
One of the major global problems is waste of product. I'm sure that everybody that is listening to me right now already struggled trying to squeeze out the mayonnaise and ketchup from the bottle or scraped out the yogurt from the tubs. In most of the cases, we just end up throwing out these plastics with leftovers in the trash can. As consequence, we have around 5 to 20% of food waste, and these containers cannot be recycled because of these leftovers. In addition to it, during garbage collection, trucks usually need to shake the trash cans in order to empty them, and that often causes their breaking. So my goal is to use solutions found in the natural world to solve these problems. I will apply biomimetic surface structures on the plastic containers that make them non-stick, or more technically, super hydrophobic. With many examples found in nature, scientists have figured out that this phenomenon can be attributed to the functionality imparted to the surfaces by the respective microstructures, which are often superimposed by nanostructures. So the food and trash plastic containers are created by injection molding. This process basically uses plastic granulates that will be filled into the machine, melted and pressurized against a metal mold. In the end, the plastic will replicate the inverse of this metal mold. In my project, I am using a femtosecond laser to create these micro and nanostructures in a stainless steel mold. Femtosecond laser micromachining can effectively create surfaces patterns on the micro and nanometer scale by using algorithms through Python software. And in order to figure it out which geometry and sizes for these structures will provide the best outcome in terms of superhydrophobicity, I have to do thermodynamic calculations. After that, I'll test this mold on a laboratory hot press, and this is where I am currently at with my project. Then, the resulting plastic inserts will be analyzed for their degree of hydrophobicity using a goniometer, and the most promising surface patterns will be tested in an injection mold of the industrial partner. In the end, I expect that from my project results, super hydrophobic food and trash plastic containers will be fabricated by the industry. As a consequence, tons of food waste will be avoided, more plastics will be recycled, and less trash bins will be broken. Thank you.
Hello, everyone. So every year, there's 100 million tons of waste activity sludge generated in wastewater treatment plant. Handling this waste costs half of the operating expenses of a plant, and it will lead to a potential global warming if only landfill this waste. So in my eye, there's a huge amount of resources out of this waste. How can we transfer the waste into energy, especially in cold climate area like Canada? Well, every reaction slows down by the temperatures. The key concept is the accelerating the electron transfer of reaction from waste to energy. So here I will introduce you a widely used technology, anaerobic digestions, which can digest waste into biorenewable energy, methane. There are 4 steps of anaerobic digestions. So at low temperature, the last 2 steps will become rate-limiting step to constrain the entire reaction efficiency. In order to increase the electron transfer rate between the last 2 steps, an interesting hypothesis will be introduced, which is called directly interspecies electron transfers. we have two microbursts, which is acetogens and the methanogens. So the acetogens can emit electrons, and the electron can directly transfer through the cellular structure or the conducting material to methanogens. Okay, so basing on this, I decided my experiment. Use zero-valent iron as a conducting material. I set 3 conditions. And I also analyzed my microbial community analysis. So for the results, as you can see, at 20 degrees, the CVI addition enhanced the methyl productions and compare the microbial community structure. Exactly, we found that acetogens and the methanogens that grows aggregates around the CVI powder. This can indicate that the diet may happen at the surface of CVI and accelerates the electron transfer. Overall, this research will make it feasible to operate anaerobic digestion at low temperature to save the energy using for heated reactor. In the meanwhile, produce more energy. Thank you very much.
Current efforts to monitor and control antibiotic resistance often focus on areas with high antibiotic use, such as hospitals and agriculture, when in fact, over recent years, wastewater treatment plants, which receive waste from these settings, have emerged as hotspots of antibiotic resistance and a gateway to the environmental spread. However, wastewater treatment plants are very complex systems. It's really difficult to determine exactly what is affecting the level of resistance. So my research works on breaking down this process to investigate the impact of specific variables on antibiotic resistance. So during this presentation, I'm going to be talking about influent immigration. That is how the bacteria within the incoming wastewater affect the bacteria and antibiotic resistance within the wastewater treatment plant. So to do this, I take a bottom-up approach, building up mini wastewater treatment plants in the lab. This allows me to investigate immigration with appropriate controls and reproducibility. I then use DNA sequencing to analyze the bacterial community, and we also look at antibiotic resistance genes within the systems too. So now let's take a look at some of the results. So here we have a principal coordinate analysis, which is basically a way of visualizing the similarity or dissimilarity of the microbial communities as a whole. So points that are closer together are more similar, and points that are further apart are more dissimilar or different. So we see that with immigration, there is a shift in the bacterial community from left to right. This indicates that the incoming bacterial community is in fact affecting the bacterial community within the wastewater treatment plant. So this may seem obvious to you, but for many years, engineers and modelers have considered the impact of immigration to be negligible. Here we're shown that this is not in fact the case. So now let's take a look at how immigration is affecting antibiotic resistance. So we saw that with immigration, there was an increase in the diversity of antibiotic resistance genes within these wastewater treatment plant systems. This included resistance to many types of antibiotics, including beta-lactams, fluoroquinolones, and macrolide antibiotics. And if you're not necessarily familiar with these classes, they're commonly used in the treatment of infections such as pneumonia, UTIs, and septicemia. So they are very clinically important. So from this, we can conclude that immigration does in fact impact the bacteria and the diversity of antibiotic resistance genes within wastewater treatment plants. My next step is to look at the factors affecting the level of antibiotic resistance within treatment plants, with the ultimate goal of being able to optimize system design to minimize antibiotic resistance. Thank you very much for your time, and if you have any questions, feel free to send me an email.
If you think the roads are bad in Montreal, well, you haven't seen worse. Here is a picture taken in northern Canada, and the reason of this disaster is not because of the workers did a terrible job, but because of climate change. Climate change has let the frozen ground called permafrost thaw and degrade. Here in Canada, more than half of the land sits on permafrost, intensively located in the north. Average temperature in northern Canada is nearly 3 times of the global average and have continued to increase. My doctoral research is specifically addressed the impact of building infrastructure such as roads, energy systems, and the day-to-day life to northern communities. My first research objective is to understand how much the permafrost thawed due to climate change. Under the ground, we can define 3 layers: the active layer, permafrost layer, and unsaturated layer. Each layer has its own physical characteristics, and I will develop a multi-physics model that simulates all the transport phenomena, including freeze-thaw cycle, carbon release, underground water flow, and mechanical deformation. My second research objective is to design a renewable energy system to freeze the permafrost. Conventionally, the system has a heat exchanger placed in the ground, but in my proposed system has a phase change material called the thermal battery, serve as the energy storage. So in winters, the system will operate fully, and the thermal battery will store the cold energy. While in summers, the system will only work below the ground, and the battery will supply the entire system. Therefore, the renewable energy system has absolutely zero energy consumption and is capable to freeze the permafrost throughout the year. Well, my research is to address an urgent issue on climate change. Well, the idea behind is about energy storage and the use of thermal battery, and it can be really going beyond. For example, if we are able to supply our stored energy during a cold day in Montreal, then it's not impossible to bring the weather in San Diego to Montreal. Thank you.
Hello everyone, today I'm going to share a data-driven PC method for PTDC evaluation, which can help to better utilize the renewable energy source. So how to realize this? We will first introduce what's total transport capability, or TTC for short. Take Hydro-Quebec, for example. There are multiple interconnections in neighboring provinces and states like Ontario and New York. Operators in Hydro-Quebec may care about how much power that can be transferred from Quebec to Ontario in a reliable manner. This power is called TTC, and it is crucial in maintaining the system's security. To promote a sustainable electric power market, more and more renewables are integrated into power systems like solar and wind farms. But solar and wind farms are sarcastic since they may be easily affected by the weather change and location change, thus introducing high uncertainties into power systems, which turns TTC a random variable called PTTC and poses challenges to the evaluation of PTTC. So how to deal with these challenges? In a traditional way, people try to run tens of thousands of simulations to calculate PTTC. Based on a CPF model, this method is called Monte-Carlo simulation. However, this method is too time-consuming, so we propose a surrogate model called data-driven PC, or DDS-PC for short. This method uses the data directly, and it requires less information. More importantly, it is about 18 times faster than the traditional method. Then we demonstrate our method on IEEE 118 bus system. 6 wind farms and 6 solar PVs are integrated into the system. Similar average value of PTTC are obtained from both MCS and DDS-PC method. The black bars show the results from MCS method, and the red bar show the results from DDS-PC method. This proves the good accuracy of our proposed method. Regarding the time efficiency, the computation time reveals that the DDS-PCE is 18 times faster than the MCS method. To conclude, our method for PTTC evaluation uses the data directly, and it requires less information and can achieve a good accuracy with less time. These are the three highlights of our proposed method, which are helpful in determination of PTTC and can help to maintain the system's security with high penetration of renewables, thus creating a more sustainable electrical power market. Thank you.
If aviation was its own country, it would be in the top 10 greenhouse gas emitters in the world. To burn less fuel and transition to a cleaner energy source, planes must be made lighter. This begs the question, how can we do so while keeping them strong? Well, luckily, this is where computers come into play, and they can tell us to take parts like these and tell us exactly where to remove material without compromising structural integrity. The issue with this is that this process generates complex curvatures, which are difficult to manufacture with traditional techniques. My research focuses on making these types of parts using 3D printing. This is a process that involves laying down plastic in thin layers, one by one, until the final part is done. So how do we go from layer by layer to final part? It starts with an extrusion head that's on a robotic arm that lays down a thin bead of plastic on a build plate. And that bead forms a layer that has a certain thickness. And these thicknesses stack on top of one another until the final part is done. So this layer by layer process has a critical factor about it. It's that these layers need to stick together for the whole part to be strong. So that the strength of that bond all depends on the temperature of the environment. So if it's too cold, the plastic will solidify too quickly as it's laid down, and it won't bond with the layer underneath. And so that will create parts that are prone to breaking, and that's not an option in airplanes. However, if the temperature is too hot, then the plastic will stay soft for too long, and the part will be prone to deforming. So we want to strike the perfect balance between strength and dimensional accuracy. So I want to find that perfect temperature. And how we do that is by printing a bunch of samples at different temperatures. So those are different test groups. And then we take those samples and we pull them apart and see what's the force that's needed to pry those layers apart. And so that force gives us the strength, and we want to pick the temperature that gives us the maximum strength. So that technique will help us make our planes lighter, more fuel efficient, and more sustainable. Thank you.
Hello, thanks for joining me today. So I'll be presenting my project on laser powder bed fusion additive manufacturing of aluminum copper alloys. So let me talk about it. Why I selected aluminum copper alloys is, if you see the image in the figure 1, that is a figure of an aeroplane, and the main part of the component that is shown in brown is made of aluminum copper alloy. You know that it's the main component of the aeroplane, and that is made of aluminum copper alloy. Why we use this is they have a lightweight, high specific strength, they have good mechanical properties, and they can be heat treated to enhance them further. But the problem is they get cracking while processing. You can see that in the image 2 below, and you can see for different aluminum copper alloys. So how I will tackle them is I'll be using additive manufacturing. So what is the advantage of it? So if I use the additive manufacturing, I will have a less material waste that is more sustainable, and I can design complex geometries and I can produce near net shape components. And so that is why laser additive manufacturing is a useful process. So let me talk about how I will be handling this process. So in the figure 4, you can see industrial Renishaw AM400 machine, which I'll be using to process a manufacturing component. And if you see in the figure 3, that shows more specific of the process, how powder is spread layer by layer and produced a component. But when I talk about this process, there are some main parameters that is represented in terms of energy that is shown below is EB. It depends on power, exposure time, and point distance, hatch distance, and the powder layer thickness. So what I'll be doing is I'll be controlling these 5 process parameters to optimize the process and produce any defect-free, crack-free, and nice sound component. So let's talk about results. And it's great that we produced a crack-free component with the process optimization. And you can see in the image left, there are lots of pores and cracks, but with optimization, I successfully produced a dense and defect-free sample that is shown in right. So that's good. So if I talk about future, my future work will be to produce larger components because this is a small component, and then I'll be doing mechanical testing to test the properties, and future will be to optimize process for different aluminum copper alloys. And great, I hope the results will be good. Thank you.
We all love to travel, going to new places, see the sky from above. But we also know, now more than ever, the impact of this type of activities on the environment. This year, we observed something remarkable happening to the world. Surface water quality has improved. We saw dolphins on the news getting closer to the cities, even a whale coming close to Montreal. Everything we do to the environment has a huge impact in nature. And that is why we need to work with processes and materials that are the most efficient with the minimum impact possible. It is estimated that 1/4 of the world's energy consumption is associated with overcome friction and wear. Friction is something we experience all the time, everywhere. Right now, you don't slip out of your chair due to the friction forces of your body touching the chair. And we can observe the effects of wear when the marks on the sole of our shoe fade with constant use. Here, you can see an airplane in the sky. If we look closer, I can show you how an engine looks like inside. This is a really complex component in the airplane, working at high temperatures and pressure, where, due to friction and wear, some of the components need to be replaced or repaired constantly. Remember those amoebas we studied in biology class in elementary school and how small they were? What if I told you that by adding a layer with the thickness of this amoeba that is in the order of microns, we could not only improve the lifetime and performance of some of the components in the engine, but we could also increase the efficiency of the turbine, reducing the overall energy consumption. My research focuses on understanding how adding this layer or coating of a cobalt superalloy performs under this severe environment. A particularity of this superalloy is that due to the continuous motion, some subproducts can be formed, a more reliable and more stable material. I am going to use a technique that is called thermal spray to produce a coating in a small scale. It's going to be the material of the component of the engine part. And in the laboratory, I am going to reproduce the friction conditions that are expected in the engine. If we apply this same coating to other means of transport that experience similar conditions, imagine the impact this could represent on reducing energy consumption, as well as the...
Hello everyone, thank you so much for watching my presentation. First, I would like to ask if anyone recognizes the unit in the picture here. That is a typical unit for high temperature solution heat treatment. Upper part is the furnace and lower is the oil or water content. T6 temper is traditionally used, which includes solution heat treatment and followed by a lower temperature of direct aging. Therefore, you can imagine that T6 is a heavily energy consuming treatment. PBF in this case. In fact, printed A357 already have a very fine and unique silicon microstructure, which will be destroyed during T6. And quenching will actually cause distortion of the part, especially 3D printed part that usually have a very fine geometry with a thin wall thickness. Since solution treatment and quenching is not efficient for printed A357 or even worse mechanical properties, here comes about my project that I would like to propose a new sustainable heat treatment on printed A357 by direct aging at temperature around 180 degrees Celsius. To test this proposal, following are the methodology that I would like to use. First, powder characterization to ensure powder quality before printing. After printing and cutting, sample will be direct aging, or so-called T5 heat treated at 180 degrees Celsius up to 16 hours. The treated sample will be investigated by porosity test, microhardness test, and microstructure analysis, respectively. Although 180 degrees Celsius treated sample hardness indeed increased around 10% in the first hour, but then decreased rapidly right after 1 hour. Therefore, I should work on investigate other temperature that can have a longer peak hardness holding time, which is practical to be used in production line. Above all, I would like to make a conclusion with a rough comparison. For a same period of time, 150 degrees Celsius solution heat treatment, 540 degrees Celsius solution heat treatment spend 4 times energy comparing to 160 degrees Celsius direct aging. In the other word, if this new method of direct aging works, it could save at least 80% of energy consumption in a heat treatment comparing to traditional T6 method, which we did not yet include the energy cost during quenching procedure and transportation between furnace. Therefore, I do believe that my project is essential for the sustainable industrial process, especially additive manufacturing is a rising star in the industry. Thank you so much for listening.
With all the climate change issues happening right in front of us, people may think that they can readily be addressed by phasing out the oil and coal plants and integrating as many renewable energy sources as possible into our electric grid. But this is not as straightforward as you think, because this is like changing the engines of a plane mid-flight without landing. In addition, the spare engines are not easy to control, as solar and wind energy manifest uncertainty and variability. My research aims to increase the ability of these renewable sources to support the electric grid by enhancing the converters that connect them to the grid. Specifically, the goal is to increase the transmit the harvested power at higher voltages, demanding additional power instead of relying on local generation by coal and oil plants. So, the conventional converters do high voltage conversion through the help of transformers. However, for this, you will need to increase the transformer volume and hence the cost to achieve higher efficiency. But recently, silicon carbide switch, one of the key components of the converter system, has achieved a major milestone. It can now be utilized at much higher voltages and much faster switching speeds. So what I do is to try to come up with converter configurations that utilize these features in order to reduce component count and transformer size. From the generalized structure of my proposed converter, 2 unique configurations were generated. From the graph, it can be seen that the 40 kilovolts DC bus voltage can instantly be attained at 1 kilohertz operation for config 1 using 6 But with the newer silicon carbide switches, its response becomes comparable to config 1 by switching at 40 kilohertz using only one transformer. For both configurations, switching from 1 kilohertz to 40 kilohertz also reduces the current distortion. Overall, the advantages are increased efficiency and future cost savings. We've been confirming these merits one by one through simulations. And as a PhD student in electrical engineering, I hope that my research can get that plane reach its destination for the sake of future generations. Thank you.
In today's fast-paced and fast-changing world, do you know something ironic? It is our world energy supply. In 30 years, it is astounding to see renewable energy stay stagnant between 12 to 14% of the total energy supply. It is also saddening since we are currently in the middle of climate crisis. Based on this 2018 chart, it is easy to say that we need to increase the supply of the renewable energy and decrease the supply of the fossil fuel-based energy. But how? My name is Putra Hanif Aksangani, and I'm studying geothermal energy. The idea of geothermal energy is below the surface of the Earth. As the depth increases, the temperature is also increasing. To utilize this geothermal heat, we can do it by sinking a geothermal heat exchanger. It works by flowing the water through the inlet, and then the water is heated by the geothermal heat, and then the water is going upward and then extracted from the outlet. However, the cost to install the heat exchanger is expensive, so we have to make sure to develop a cost-effective heat exchanger. One of the most important phases to do that is to enhance the efficiency of the heat exchanger. So the way I did it is by modifying the closed-loop model into semi-open loop model by forming a porous structure by controlled fracturing the rocks at the bottom of the well and numerically investigate it. The hypothesis is by adding porous structure, the contact area is increased and the conduction convection mechanism is also enhancing the heat transfer rate. To ensure the validity of my research, I validated my model with the experimental results of closed-loop model in Beppu, Japan. It is validated. It is based on the inlet-outlet temperature difference in regards of time. The conventional closed-loop model can heat the water by 15 to 20 degrees Celsius. Then, I make a comparison with my optimized model between the closed-loop model and semi-open loop model with the exact boundary and initial condition. But the only difference is only the porous structure at the bottom of the well. It can be seen that the semi-open loop model increased the temperature by 5 degrees Celsius. The results show that the previous hypothesis is correct. Higher temperature leads to higher generated power by the heat exchanger. While the study shows that the semi-open loop model can improve the performance of the heat exchanger, follow-up study is still needed and undergoing to find the most optimal model of the semi-open loop heat exchanger. Increasing the renewable energy supply should be collective works by many people from different backgrounds. Hopefully, in the next 10 years, the growth of renewable energy won't be stagnant like the previous 30 years. Thank you for your attention.
Look at this graph. What does it look like? Some might say it looks like a duck, and they are right somehow. But this is in fact the curves that show the changes in the power demand in California from 2012 to 2020. You can see that in 2020, the power demand decreases around the afternoon until the sunset, and suddenly it increases significantly by 6 p.m. in the afternoon. These significant ramps are caused by so many solar panels installed in California in the recent years, which is kind of good news. But this curve is not a good thing for the power grid performance due to the rapid changes in the power demand in the morning and evening. So the utility centers, they require to turn on and turn off the other power generation plants continuously, which is not efficient, and sometimes it's not even possible. So the question is, what is the solution? Well, we have few solutions. The first solution is we can build new fossil fuel-based fast-acting power plants, which will solve the problem. But this will waste the whole purpose of adding solar energy. The second option is adding a large energy storage system in the power grid. However, this method is also very costly and require a lot of maintenance. The third option is using electric vehicles. But how? So it is projected that in 2030, more than 30% of new car sales will be electric vehicles, which is around 8 million cars a year. So you can see it's a great potential there for using EVs for this purpose. It is called vehicle to grid mode. My research is on how to provide vehicle to grid services using EVs in the charging station. Well, it all goes back to the control design of the charging station and the EV chargers. Right now, I'm working on autonomous control design for the EV chargers to aggregate all EV batteries with different state of charges and capacities without requiring a central controller or high-level communication. But how I do it, I'm using adaptable Drew coefficient based on the EV state of charge to balance the EV's state of charge while allocating the charging or discharging power among EVs based on their power and energy capacity limits. So this Drew coefficient creates little voltage changes at the reference voltage at the feeder. Based on this voltage drop, the local controller in the charging station calculate the required discharging or charging power. And with this method, we can aggregate all the EVs in the electric vehicle mode. Using this method, we can have a high capacity energy storage system that store the available PV power in the afternoon and release this stored energy in the evening, and basically flatten the duck curve that we have in California without the need for a new power plants or energy storage system. Finally, although there are still many other challenges with regards to the control designs and the policy development to provide vehicle-to-grid services, deploying EV batteries in vehicle-to-grid mode can ease the usage of renewable energy resources. As a result, we can get closer to the dream of having emission-free power generation and create a cleaner environment for ourselves. Thank you.
Thank you to all the students for their hard work in preparing and delivering their presentations. And I'd now like to introduce our judges, which were tasked with selecting our 2021 changemakers. Our selection committee was composed of 3 faculty members. 2 members of the panel come from industry, and one of the panel members is a previous changemaker, who from the original SED Talks program. The industrial representatives are Jamie Summers from WSP, who is involved in the Future Ready program, and Avram Goldman from Pratt & Whitney, Canada. The faculty members are Professor Salman Craig from the School of Architecture, Professor Noemi Manuel Dorval-Kurchen from Chemical Engineering, and Professor Xiaojie Wang from the Department of Electrical and Computer Engineering. And our past changemaker from the 2016 SED Talks program is Jen Yin, who is a postdoctoral fellow at the Max Planck Institute. Now, normally when we hold this event in person, this would be the moment where the judges would meet to deliberate and the audience would mingle and enjoy some food and beverages and yes, maybe a beer. And but because this year all things are virtual, and since we had the students record their talks ahead of time, the judges have already done the deliberation earlier this week. The discussion was comprehensive, and in their decision, the judges considered a multitude of factors, including, of course, the content of the talk, and the delivery, the body language, the voice projection, stage presence, etc., as well as the effectiveness of their visual aids and slides. But the judges also considered other factors, such as the student's topic relevance to sustainability and how it fits with TIZED's mission, representation across the various departments and topic areas within the broad area of sustainability research that's going on within our faculty, both historically as well as in the current cycle. And of course, we also considered equity, diversity, and inclusion in this selection. So after the comprehensive review, I'm happy to announce that the judges selected the following 3 students as the 2021 changemakers in no particular order. The students are Christopher Ramos, Breno Mumik-Sakara, and Claire Gibson. And congratulations to all of these three changemakers, and I look forward to working with them during the winter semester towards the SEDtalks program. At this point, we're going to move to the Audience Choice Award, and for this, we need all of you at home to participate. So we should have a link to the survey coming up onto the screen, at the bottom of the screen. Please go to the website and vote for your favorite presentation. The winner of the Audience Choice Award will receive a $200 prize, and you will notice that the list doesn't include any of the three students named as our new changemakers, as they are not eligible for this award. So while we wait for the votes to roll in, I would like to take this opportunity to say a few words of thanks. You'll have about 2 to 3 minutes to prepare to make your selections. First, I'd like to thank again our students for their presentations. I'm sure that everyone who joined us tonight has learned something new and gotten a sense of the breadth, diversity of the sustainability research going on at McGill, as well as piqued your interest, I hope, into this. And we wish each of the students success as they complete their projects and carry on to hopefully become agents of change in our society. On behalf of the presenters today, I'd like to extend a special thanks to our entire selection committee for their time and involvement in this event. And I'd like to thank the TIZED team, as well as McGill's Media Services team, for their efforts in helping coordinate and organize this event, which is even more challenging than usual given the circumstances around the pandemic. I'd also like to thank the skill set staff at Teaching and Learning Services here at McGill, who offer customized support for the learning and work with all of our students in developing their professional and communication skills. And I would especially like to acknowledge the important efforts of Andrew Churchill, who led the fall workshops and worked with our students throughout the past several weeks. The work of TIZED would not be possible without the strong support from our donors, as well as our industry partners. So with that, I'm going to give another 30 seconds to a minute to complete the polling. It's looking close. I'm going to give another 30 seconds or so. Well, it looks like our audience choice member for the audience choice winner for this year is Putra Hanif Agsan Gan. And so congratulations to you, Putra. Thank you to everyone who voted. And that concludes our evening. On behalf of TIZED, I want to thank each and every one of you for being part of our SED by 180 Seconds event tonight. We hope that you can all join us in the spring for the SEDtalks event, where we'll have a chance to see our 2021 changemakers present a more comprehensive talk on their research. If you're a graduate student in the faculty and are interested in participating in the training program next year, please visit www.mcgill.ca/TIZED for more information, or feel free to contact TIZED at mcgill.ca. Thank you, everyone. Stay safe and good night.